Hello everyone, my name is Andrew Gryguc and I'm from the University of Waterloo, which is just outside of Toronto in Canada. It's with great pleasure that I'm presenting this talk today in the very first European Conference on Fracture. The focus of my talk will be a method for comparing the fatigue performance of forged magnesium components. I'd like to acknowledge the support of the funding agencies and industrial partners who made this work possible. This particular presentation is detailing the nuances of developing a comparison method for fatigue performance of forged AZ80 magnesium alloy, but it's part of a larger project where we actually designed, analyzed, optimized, and manufactured automotive suspension components from magnesium for vehicle lightweighting initiatives. So this presentation will aim to summarize a holistic approach we adopted in this research project known as the Integrated Computational Materials Engineering, or ICME approach, which is an approach to design products and the materials that comprise them and their associated processing methods via linking the material models at multiple length scales. You will see results from this talk spanning the full range of length scales illustrated in this diagram, but in general I'll focus on the micromechanics of the research and then gradually zoom out towards the system level to see how the process structure property performance relationship interacts with the knowledge development at each of these length scales. Somewhat of a prelude to the talk, I like to present this photo of the final component which was produced as part of this work, not only because it might be visually appealing, but to emphasize the main objective of the work, which was vehicle lightweighting. We targeted a fatigue-critical automotive suspension component, which we were able to achieve a 37% reduction in mass versus the aluminum baseline component. This type of paradigm-shifting improvement was only possible due to the experimental method which was adopted to optimize all facets of the research process. On the left-hand side of the slide, you can see a schematic of the forging process where intense pressure between rigid dies forces the material to flow in these internal cavities and conform to the desired component geometry. This can have many beneficial effects for fatigue and some detrimental ones if the process is not carefully managed. And this is done at moderate temperatures between 250 and 450 degrees Celsius. So the process being managed is a highly thermomechanical equation to satisfy. An overview of my talk can be divided into three sections. The first two deal with understanding the effect that the starting material has on the fatigue of the forged AZ80 magnesium alloy. The second is the effect of the most significant processing parameters being temperature, strain rate, geometry, lubrication, orientation within the die, etc., and how they play a role in the fatigue performance of the final component. And then finally, I'll follow up with a more detailed method of comparison using fatigue data that we've developed and characterized to understand how to design a forging process that will result in a desirable component with desirable fatigue properties, and then understand the variability that's associated with forging real components. So now that was a lot of information regarding how we went about the project. However, to summarize and better understand the structure-property relationship, I've distilled all of those phenomena that I previously discussed down into a few key elements. Firstly, the obvious comparison of what is the difference between the starting the forging process development with a cast or extruded material. On the left, you can see the monotonic tensile response of the as cast and the as extruded material. AZ80 is the alloy here of magnesium in all the different material directions. You can observe that the cast material has identical material properties in all three directions, differing from the extruded material, which has anisotropic behavior. And you can see that in the varying material responses here in the two different directions. Furthermore, there's an obvious difference between the two, with the extruded material having a much higher strength and enhanced ductility, which is typical of rod forms of magnesium alloys. Secondly, these observations are supported by the comparatively higher superficial hardness that's shown in these contour plots on the right here of the extruded material once forged. These are shown on the same 30-ton Rockwell scale here. Due to the complex cross-sectional nature of these forgings that were investigated, there's a pronounced spatial variation in the properties. So this is a topic I'll discuss in more detail. These are just I-beam intermediate type forgings here. It's not a full component scale forging, but I will be discussing that towards the end of the presentation. Now, extending this comparison towards the fatigue performance of cast and extruded AZ80 magnesium, As one might expect, there's again a dramatic difference between the two, as was indicated in the tensile monotonic curves, which is deeply rooted in these contrasting microstructures between the two, the different textures, leading to vastly different material responses and cyclic responses. It can be observed that under strain control fatigue testing, in the high cycle regime especially, for a given strain amplitude, the extruded material has a life which is superior to the cast material by a factor of more than 10, or an order of magnitude. Now, the second phenomenon which I'd like to discuss is the effect of forging temperature on the monotonic behavior, which is by far the most significant process parameter. You can observe that in general, higher temperatures have enhanced ductility, as we can see in the images on the right here. However, at the cost of lower strengths. Furthermore, the increase in material properties is obvious between the as received and the forged materials. So the forged materials generally are indicated by the colored lines, and the as received are the black lines. Linking that back to a previous observation, the superficial hardness correlates well with the yield strength of the material in various locations throughout the cross section of the forging. As you can see, location B generally has the highest yield strength, which is this center region that has the highest amount of strain due to forging, and it has the highest amount of superficial hardness. The other important observation is how the base material is modified due to forging. There's a much more pronounced improvement due to forging with the material when you start with as cast material, whereas the improvement with wrought material as the base material, being the extruded material, is more marginal, as one might expect. Once again, it can be observed that under stress control fatigue testing now, so a different method of comparison, in the high cycle regime, for a given stress amplitude, the extruded material has a life which is superior to the as cast material by more than 10 times, as you can see here. Important to note is that the materials being compared are from a full-scale forged component, so the effect of the processing temperature is really the most important in the last step of the thermal history prior to the in-service use. So, i.e., this isn't the extrusion temperature of the material prior to forging, but it is the die forging temperature and the subsequent cooling schedule after forging that governs the final microstructure. Although we did look at a post-forging heat treatment in this particular project, I've chosen not to discuss them here as they're very alloy and application specific. So you can simply think of the analogy that the final heat treatment will govern the resulting microstructure, as it does in many materials that we utilize in engineering systems. Um, the precipitate content is also governed by this final heat treatment and the morphology of these precipitates, as well as the final properties. If no specific heat treatment is given, it's the last step of the thermal history during the forging process that effectively is replacing this heat treatment. So as you can imagine, the physical component is a complex three-dimensional shape as indicated here. So thus the local strain and thermal histories throughout the component can spatially vary. And we looked at characterizing all these different locations. So there was 18 different samples in these particular components to understand the spatial variation in more depth. So now overlaying all these individual data points that we've collected over the SN curve, one can easily appreciate that even at the component level of forging, a large amount of variability occurs in the properties, which is highly a function of the location within the forging itself. So indicated by all these numbers are all the different forging locations within this component. For reference, overlaid on the curve is a design curve, so that's these dashed lines here, for the benchmark aluminum, which is this dashed black line here, which we can see um, is easily exceeded by these two other forgings that were done. Only by the forging that was done at 300 degrees Celsius do we get a superior property, however. This provides confidence that if we get the forging parameters right and the process control right, we can meet or easily exceed the baseline performance in fatigue for this particular component being an A356 aluminum alloy. So now looking at the effect of forging design, so between all the different forgings that we've investigated, we've looked at a variety of different forging geometries and configurations. Here we can see a dramatic improvement in the fatigue performance of the as cast material once forged in a simple upsetting technique to produce these types of flat forgings here that do not restrict the material flow in either direction. So this is a substantial increase in material properties that's typical when forging cast varieties, as I previously discussed, of magnesium, which the benefit basically is coming from the refined equiax microstructure, which is resulting from the thermomechanical processing. However, when we look at the extruded and forged material, which was forged in a totally different configuration of forging now, which was this closed die I-beam type shape, the differences are not quite as simple. Since the starting material was wrought to begin with, there is a more modest modification of the properties due to forging. In general, an improvement is always observed in the high cycle regime, as seen here. However, at lower forging temperatures, limited ductility in the material might cause a small degradation in the strain control fatigue behavior, as we can see here. Finally, when we compare the strain life curve for all of the various styles of forging, we can observe that once again in the high cycle regime, the full scale component is actually superior to all of the other investigated conditions. This is critical as the majority of the loading history for this particular application in the service loading will be exercising this kind of mid to high cycle regime of the strain life curve. So we're particularly interested in that particular location of the strain life curve. So now, as one might think, simply because the final forging process is superior to the intermediate steps which we looked at, so the different styles of forging and the different temperatures and the different forging configurations and the different base materials, does it really mean that we've fully optimized this process from a holistic perspective? So I definitely would like to ask that question and say that it's a very excellent question. So now you might be asking yourself, is deciding upon a comparison method to optimize the forging technique really as easy as just looking at all the response curves that we were just looking at as what I previously discussed? Although some very powerful general conclusions can be drawn, the results which I showed really depended upon the method for which you choose to compare the different variables related to fatigue. So now if we keep that in mind, I'd like to move forward and discuss how to effectively compare the material behavior and quantify that variability. So for the first basis of comparison, it begins with the actual loading history for the application. So the loads will be realized as stresses and strains within the component at the material level. So the application is a automotive suspension control arm, as we can see here. So in order to simulate this type of real world behavior, we implement a variety of different laboratory style tests, which use fully reverse loading over a wide range of amplitudes to characterize the material behavior. As the vehicle undergoes kind of individual cycles within the fatigue block, as we can see here, the material is undergoing cyclic hysteresis as indicated by the loop on the right here. The first approach employed is to use the stress reversal as the basis here. So we can see that indicated at the top and bottom here for characterizing the fatigue life. So if we impose the minimum and maximum stresses as the boundary conditions for the experiment, then we measure the resultant material response. So the key output for this is an SN curve from this style of test. The second technique is to control the maximum and minimum strain amplitudes and measure the stress response of the material. So the key output from this style of test is a strain life curve, which is generally used to model the material behavior in the automotive domain. Finally, we can also use an energy quantity, so the strain energy density, as a basis for comparison. And by energy, effectively what I mean is the combination of the elastic or the reversible strain energy density signified by this gray triangular area on the right, and the plastic or irreversible strain energy density is signified by the yellow area enveloped within the hysteresis loop on the left. So now the argument can be made which technique is most representative of the actual loading in the service environment of the vehicle. And the answer is, well, it depends. I'll go through and discuss what these comparisons yield when looking at the full-scale control arm forging that we've discussed earlier and the conclusions that we can draw from the spatial variation in the properties within each. What you're looking at here is the first case. So it's a comparison technique by the method of stress control fatigue testing. So recall that the SN curve that I presented earlier with all the data points that were scattered around that's shown on the right here. So the design curve in the middle, which is shown by this equation here, represents kind of the average material behavior, with some locations on the control arm having a life which is above this kind of idealized response. So everything to the right of this curve here. So if we non-dimensionalize these data points with ones that fall to the left being kind of worse than the idealized response and ones that fall to the right being better, once we non-dimensionalize these relative quantities, we can effectively get a life multiplier that describes how much each location deviates from this idealized response. So these are the life multipliers here shown on the contour plot, we can then map these onto the various locations of the control arm and understand the spatial variation. It can be seen that in location 1, near this region of the line here, a location which is a topic of further discussion in another presentation actually in this virtual conference. It has the lowest life multiplier with a life that's over 4 times less than the idealized behavior. Whereas location 9 on the other side of the arm shows kind of the converse effect, where the design curve is conservative in its fatigue prediction. In general, these internal regions here, which are kind of the web regions of this I-beam of the control arm, between the flanges on the upward side of the arm, have kind of superior fatigue performance, as you can see here. Similarly, we can do the same thing for strain control fatigue test being the method of comparison, and we can draw a few more conclusions. Firstly, the contour plot scale here has been exaggerated to highlight any differences throughout the arm, but you can see that in general, when comparing the spatial variation using a strain control approach, the multipliers are much closer to a value of 0, indicating that the design curve more accurately represents the material location, which is a good thing when we're using this for fatigue life prediction. Important to note, however, is that the critical region, which was location 1 in the arm, as indicated in this image here, is still the region with the lowest multiplier or the most non-conservative prediction. This provides confidence that in the fact that both comparison methods that we've investigated so far indicate similar trends in the behavior. Finally, when comparing on an energy basis, the story is similar to the previous slide, where the contour level is even further exaggerated to highlight these differences in the spatial variation throughout the control arm. Any differences observed here are more closely linked to defects within the material, as the spatially varying thermomechanical history would manifest itself as a different level of cyclic strain energy density. So we can see a much closer representation of the design curve to all of the data points being very much not scattered or scattered very closely around it. So to summarize how one might select the optimum forging condition based on all of this information, we can utilize a number of metrics. Since the fatigue response is the focus here of this particular application, I'll discuss how varying the processing parameters affect the strain control fatigue response. The strain life curve presented here is for both forms of magnesium alloys, cast and extruded. Now we can recall that the extruded material is textured and will exhibit an asymmetric cyclic response. Accordingly, you can see this induces anisotropy in the fatigue life. In the strain life behavior as the curves vary between the extrusion and the radial direction for the exact same material. So that's important to note here, the ED and RD directions of the extruded material. Next, adding the as cast open die forged material curves, we can observe that the dramatic improvement being observed realized especially in this low cycle regime. So, but fairly much across the board. Finally, we can introduce the optimum forge condition that illustrates a very dramatic improvement over all the conditions, especially in the high cycle regime at strain amplitudes less than 0.5, which once again is where we are desiring kind of high fatigue performance for this particular service loading. Finally, as a sanity check, benchmarking these responses against kind of the state-of-the-art material for these types of structural components, which is a 6082 T6 aluminum, we can observe that the forged material can meet or exceed kind of this baseline target for strain life behavior. Now, what you saw previously was just a snapshot of one form of comparison to evaluate which processing condition is optimal. Given the practical requirements of engineering application, an optimization function was developed that incorporates 3 different non-dimensional variables, which incorporates various aspects of the material characterization into one function whose objective is to maximize its value and obtain optimum performance. The first term, which is phi1 here, describes the necessity of the component to have a high strength and toughness, non-dimensionalizing these individual property attributes to have against the maximum observed over the wide range of processing conditions allows us to have a term which reaches a maximum value at a unity or a value of 1. The second term incorporates the fatigue behavior in terms of parameters extracted from an SN curve. Finally, since this is because fatigue, since fatigue is a defect-driven phenomenon, we can, which can be governed by the limiting location within the component that has the most inferior properties, as we illustrated in the previous slides. The spatial variation of the hardness of the component was also considered to ensure we selected a processing condition that produces a uniform component with uniform properties that are free of major defects. So now calculating the magnitude of this objective function shown up here for all the investigated processing conditions, and the following surface plot can be generated for as cast AZ80 magnesium and as extruded AZ80 magnesium that was then later forged for both cases. Once again, a value of 1 on this surface is technically considered to be optimal. So we have strain rate on one axis, forging temperature on another axis, and optimization parameter on the z-axis, which is effectively representing how optimal that particular forging condition is. So selecting an optimum condition here would be the extruded and forged material process at 250 degrees Celsius and a strain rate as fast as pragmatically possible of 10 per second. Important to note here is the fact that the weight factors that have been selected here, so these coefficients, were specifically tuned for this engineering application that we've considered here, but effectively can be retuned to meet the requirements of other structural components. Finally, if we impose some constraints upon this optimization surface, such as the fact that at the extremities of very low temperatures and high strain rates, we observe cracking defects, as you can see here within the material. Secondly, at temperatures that exceed 426 degrees Celsius, which is including the heated deformation, that's the incipient melting temperature of the material, and that can result in inferior properties. So we might exclude that region from the processing domain as well. Finally, the practical constraint of forging press loads can prevent forging at a very low temperature, even at comparatively low strain rates, just because we run out of, it's not pragmatic to forge at such high loads. This effectively limits our processing window and generally will constrain the optimum forging condition to be a compromise of all these pragmatic conditions. So you can see how the optimum forging condition will move from this location here to slightly here once we impose the constraints. Furthermore, although not very significant in AZ80 magnesium, the cost differential between as cast and as extruded forms of base material might make another option seem more attractive if cost saving is can justify the degradation of performance that's typically realized with starting with cast starting microstructure. So some concluding remarks: a stress, strain, and energy-based fatigue approach were used as a basis for comparison of the durability performance of forged AZ80 magnesium components. Secondly, the optimum processing conditions which lead to the most desirable fatigue properties are highly dependent on the in-service application that's being utilized or that the component's being designed for. Finally, an optimization function was developed for an automotive fatigue critical component, which was utilized to select forging process parameters which result in optimal performance. And with that, I'd like to thank you for your attention and open the floor to the audience for any questions. In closing, I'd like to challenge the audience to tell me a concern that they may have as researchers towards using magnesium as a material for fatigue critical components. I would very much like to collaborate. Here are my contact information at the bottom here, and I very much appreciate the opportunity to collaborate in this online medium and this virtual conference. Very much thanks, and thank you again.